welcome to the Academic Fringe Festival. My name is Jay, and I'm an assistant professor in the Web Information Systems group at TU Delft. I also happen to be a co-director of the Delft AI Design at Scale Lab, so which is also the theme of this speaker series, Design at Scale. So with Design at Scale, we discuss ways to combine the creative power of humans with the analytical capabilities of machines in the design and development of systems that can help us tackle societal challenges at large. This week, I'm thrilled to announce our speaker, Tim Kraska, who I came to know more than 10 years ago, actually, while reading his pioneering work, RocksDB, that for the first time proposed to leverage human intelligence at scale via crowdsourcing for answering queries that are difficult for the machines. So Tim Kraska is an associate professor of electrical engineering and computer science in MIT's CEST lab, and also co-director of the Data Systems and AI Lab at MIT. So he's also a co-founder of InkBlink Analytics. Currently, his research focuses on building systems for machine learning and using machine learning for systems. So before joining MIT, Tim was an assistant professor at Brown, spent some time at Google Brain, and was also a postdoc in the AMP lab at UC Berkeley after he got his PhD from ETH Zurich. Tim is a 2017 Alfred Pritchard Sloan Research Fellow in Computer Science and received several awards, including the RioDB Early Career Research Contribution Award, the VMware Systems Research Award, and many other awards, including several Best Paper and Demo Awards at RioDB, Sigmod, and ICDE. So without further ado, let's welcome Tim. And thanks a lot, Tim, again, for being here.
Thanks for having me. It's a real pleasure. And thanks for the introduction. Let me share my screen here. Okay, so what I'm going to talk about in this presentation is mainly like the recent work we are doing around instance optimized data systems and some of the algorithms and data structures we developed so far for it. So in general, the area I'm interested in is either building systems for machine learning, and we had like a large project there which was called North Star, which started at Brown University, and then we continued at MIT. And recently that actually became a company called Einblick.ai. Even though the research around that at MIT stopped with the company, I'm still a big fan of what they're doing, and I encourage everyone here to actually go to the URL and try it out, because we just launched a public offering that you can just sign up. There's no fees attached to it, and I would just love to hear your feedback. So you don't have to buy anything. This is not a sales call. It's really just to get your feedback on what we are building there, because it's so new. However, this talk is mainly on the other side, which is just like, how can we leverage machine learning to improve systems? And what I will talk about is just like in general a range of like ML enhanced algorithms and data components we developed over the last couple of years, but then also at least show you some early results on a system we are currently building called SageDB, where we bring all these like different components together into an entire end-to-end system to hopefully get like unprecedented performance. So why are we doing that? Essentially, like this whole area is based on like two facts. On one hand, Moore's law is coming to an end. This shouldn't be anything new. A bunch of people already talk about it for years, but it's becoming a reality. So the speed of processors is not improving anymore at the same pace than it used to. At the same time, data is actually increasing much faster than it has ever before. And we see now like zettabytes of data produced almost like every single year. So how can we tackle that? One way to do that is specialization. And we already see that happening on the hardware front, right? On the hardware front, we have like things like GPUs, TPUs, FPGAs, which are like specialized hardware so that you can overcome the end of Moore's law. What we are asking ourselves is like, can we not do something similar on the system side as well? And the core idea behind this idea of like specializing a system is also not something new, and it has been done already like for a long time in the past by having, like, for example, in the case of databases, specialized systems for different types of workloads. For example, we normally talk about that there are operational database systems like HStore or Oracle. Then we have analytical databases like Snowflake, Redshift and Co., streaming database systems, and so on. Each of these systems was designed for a particular type of workload, like let's say transaction processing or more analytical processing. Yet we want to go further than that. We want to hyper specialize them, because even with this like type of workloads or the systems which are created for types of these workloads are still general purpose systems. So you still use the same type of Snowflake instance for, let's say, Walmart than a bank, right? It's not like that you have a specialized analytical database just for the Bank of America, which is differently designed than the system, let's say, for Walmart. Even more, you still use the same like system, even though maybe the requirements on a Black Friday sale might be very different than any other day of the week. Right? What we want to go after is really specializing them in the extreme case to the workloads of Black Friday, which is arguably probably very different than any other day, and then self-adjust again to like the workload on the day after and or usual day on like during the week, which is nothing special. So how can we do that? On one hand, like any system you develop, essentially, like, you know that you make compromises and you want to give some flexibility to adjust the compromises, like based on the particular scenario and, for example, the hardware you're running on or the workload to expect. So typically, if you have a system, there are a bunch of parameters or knobs which you have to tune, right? Like page size is a typical one. In some cases, you can switch out the scheduling algorithm and so on. Traditionally, these knobs were tuned by database administrators, right? But nowadays, like, we go more and more into this area where those are actually automatically tuned, often using some type of machine learning technique. And this is becoming a reality. For example, Microsoft SQL Server, Amazon Redshift, they all have some form of automatic tuning right now, which observes the workload and then adjusts the knobs accordingly. Yet we want to go beyond that. And what we have been working on over the last couple of years is something which we call learned components. So the idea here is that we fundamentally reconsider the component of a system, let's say scheduling, query optimization, indexing, and figure out, okay, how would we design this component to make it possible that it self-adjusts to the workload as well as the data distribution. Right? Like having this in mind. In an extreme case, you might actually just, or like in the simplest case, sorry, you might actually adjust the numbers of knobs that it has. But in some other scenarios, maybe you can replace the entire components through a machine learning model and design something fundamentally new with this adaptability in mind. Eventually, we want to take these components and just combine them all together into a system which we call instance optimized. So the idea is that just not like replacing a traditional component in a traditional system through machine learning enhanced algorithms and data structures, but rather really reconsider the entire, let's say, database system with this like instance optimization in mind and combine several things together so that they provide like unprecedented performance, something which wasn't able to achieve before because the system self-adjusts to the workload as well as the data in ways traditional systems can't. So ideally, we want to go or get as close as possible as a hand-tuned solution for a particular workload as well as data distribution. So when I talk about instance optimized system, so on one hand, yes, we leverage machine learning where it makes sense, but it doesn't have to mean that we only apply machine learning for systems. In many, many other cases, just like traditional good old optimization algorithms and so on, or like even heuristics are the right choice. So we define this area a little bit more broadly than just ML for systems. So for the rest of the agenda, what I first would like to do is talk a bit about like some of the learned components we have been working on over the last couple of years, then give you a very brief overview about a system you're currently building called SageDB, which brings many of these components actually together, and show you some of our early results regarding end-to-end performance. And then, as time permits, talk a little bit about future directions and where we are going, as well as like opening it up for discussion. So unless there are any questions, and I'm more than happy to take them on the fly, I go on. Any questions so far? How do you usually like to do it? Questions at the end, in the meantime? Any preference?
Generally they do questions at the end, but if you like to take them on the fly, then I encourage everyone to, just use the raise hand feature and we'll try and field them as they come.
Yep. Normally I like to keep it always interactive. It's most fun. Okay, so moving on to the Learn component. So over the last couple of years, we have been working on a range of like different Learn components, from indexing, query optimization, Bloom filters, and so on. And of course, we are not the only ones working on them. Here in this talk, I will focus on 5 of them and just give you a high-level overview on like how these work and how this like Learn components came together. Again, there are many others out there. I cannot go into much depth. Just like this is really just to give you a feeling for I was just muted. Is that possible?
Yeah, sorry. Someone joined and I tried to admit and they left right away and I clicked the wrong thing.
Okay. Do I have to repeat or everything good?
It looks good to me. I just
okay.
you can go ahead, Tim.
Okay, I will go ahead. So like the first thing I want to talk about is just like this idea of like learned indexes, which we proposed like in 2017, 2018. So the core idea behind them is like, so if you have like some data like this one here, this is just an example, a table consisting of some ID, a bunch of like user orders, which like have addresses, names, phone numbers, and so on. And let's assume for the moment you want to create a data structure to efficiently look up this data. Right? And for simplicity, I just assume for the moment we only want to look up the ID column, which is just like created by an auto increment. And I assume further there are no updates or no inserts. Everything is into my memory and stored like a very big array. However, I make one qualification request here, which is just like it's that we want to support queries for ranges as well. So for example, we want to be able to ask for all the orders which have a starting ID of like, let's say 2000 to 2200. So in this case, the traditional way how a database would handle it, to index this data to provide fast access to it, is a B tree. And it's just like a tree structure you build over this ID column. However, if you look at this ID column, you notice like, yeah, they're actually created by auto increments, a very common thing most databases do. So if I know that fact, I could actually, in this particular case, do something more specific. And that is, I can take the ID, I know the first ID in my set, so I subtract it, which would give me an offset into the array which stores all the data. Right, so for this particular case, given that I know the IDs, I know what I want to index, and I know they're all auto increments, instead of using this like general purpose structure of a B tree, I can just transform it into this like offset calculation and look up the ID in the array like that way, which of course is much, much faster. Like now it reduces down to one addition, and the whole data structure only requires one integer to store, right? The starting ID, and that's it. Obviously, in other columns, this might not be possible because this one was so simple because it was just like an auto increment. But let's assume for the moment we take a little bit more realistic example that we want to index all the orders by date. So the only thing I'm supporting right now is date lookups. I assume for the moment that all the orders are actually sorted by date. So this is an assumption I have here, and I will relax that later on. And now let's assume, like again, I want to index the date column so that I can ask, for example, for all the orders happen in January 2019. Okay. So in this case, they are clearly not auto increments anymore. However, I can use a very simple observation here, and that is like if I would have a model which describes on how many orders are coming in over time, and I build the CDF of that. So like I have the community distribution function as a model, which just tells me, okay, the probability mass of the numbers of orders before simple date, I can still do this offset calculation as before, right? So like I can take this model which describes the CDF, which gives me a probability mass here. And then if I multiply it with the numbers of records I have in total, it gives me an offset into this array where all the data is stored. If the model would be perfect, this lookup using this CDF distribution like would immediately work, and that's the only thing I have to do. It gives me the offset, I find the data, I'm done. Assuming the model is not perfect, like I cannot perfectly describe the CDF, I actually can do some localized search to the left and right to actually find the data. Right? Here again, I assume that all the data is sorted by the key. Right? So like I know that everything is sorted, and using this approach now, like given that it's sorted, like searching left and right will guarantee that I will find the data without requiring that I go over the entire data set. As more precise the CDF model is, the less searching I have to do. So the idea I showed before of this like ID offset calculation, the subtraction, I use the same principle here now that except that I pass it through a model instead. So now comes the question like what types of models you can use, and the answer is essentially anything which works. Right? So you can use the whole machine learning like library and play around with just like, okay, what works best in what scenario, and use all the machinery which has been developed in the past applied to this problem of indexing. Of course, many of the models might be way too expensive, right? And they always have this baseline of just like a B-tree structure or like doing binary search. However, in certain scenarios, maybe you're able to find models which are faster than these traditional data structure. So like particular what we found is that this idea of like a mixture of experts works particularly well. So how is that created? So like normally we have one model which is trained over the entire data set. And then based on the prediction of that model, it picks another model which is trained of a subset of the data. Right, so you have a general model which makes a prediction, which then picks an expert based on that prediction, and the expert knows a certain sub area. In the case we would use more like linear models for these models, like the entire inference code for a two-stage, what we call recursive model index with linear models is on the right. So what it does is just like we first train one linear model over the entire data, which is one additions and one multiplication. And then based on this prediction, we get the weights of the second model, which is again like an intercept and a slope. So we need to do an array lookup and then again do an addition and a multiplication. And then we get the final estimate, which we then use put into the localized search in the case like the model is not perfect. So in the extreme case with the two-stage RMI with linear models, we transformed the whole thing of the lookup into two additions, two multiplications, and one array lookup to get the weights. If you ever implemented a B-tree structure, it should be very clear that the right thing is like way, way faster, because B-tree normally consists of a whole bunch of if statements you have to do, where you have to traverse every single node and then follow pointers down and so on. This on the right can be much, much faster, and you have a lot of freedom how you configure it. For example, you can also say like the tuple should be linear, it should be something more complex, which better fits the function, and so on. Yeah. So by now, this is not the only approach. There are many, many others out there. For example, what became also very popular is doing radix splines. So these are not top-down trained models. Those are bottom-up trained models where you fit splines through the data first, and then you try to index them. Again, there have been a bunch of different proposals on different type of models you can use. Overall, what that still means is like we took a traditional B-tree, the traditional approach, and replaced the thing with a model and then some correction mechanism so that we can give the exact same semantic guarantees. So important is this is not an approximate data structure. It gives you the exact same interface and API and guarantees than the traditional B-tree counterpart. When we tried that out in like 2017-18, we actually found that like compared to some of the other like B-tree structures we were able to find, which were also read optimized like fast, we were often a factor of 2x faster, but we were orders of magnitude smaller in index size. And the size argument is actually something which becomes important later on. However, when we like proposed that out there, this was just an idea. And of course, there were like many different things missing. And when we published the paper, it actually was pretty blown up on social media. And a bunch of critics actually rose from the question of like, okay, there are a lot of other baselines missing, so you should compare against my favorite XYZ index structure. The theoretical foundation is missing. You don't have update support yet. It's not clear on how these results actually impact a real life system. Right? This was like 4 years ago. A lot has changed since then. And I just want to give you a quick update where the state of the art is. So on one hand, we did an exhaustive benchmarking study with TU Munich together, where we actually took like 3 different types of learned index structures, RMIs, PJMs, and radix splines, and compared that against a whole range of traditional indexes, everything we believe is state of the art and has a shot competing against it. We also included some more recent ones like history, which is not shown on this plot, but we have them on our webpage, which was like something very recently proposed, trying to get similar to performance as RMIs, but like under fair conditions, we couldn't replicate it yet. Overall, what we found is that like in the learned structures are indeed faster and smaller. So what you see here on the x-axis is the size of the index, and on the y-axis is the lookup time. So where you want to be is the left bottom corner. What you see here is also for like 2 data sets. The blue line, which is like the RMI structure, is actually dominating everything else. Most traditional data structures you actually find on the right upper corner. So they're really not competitive. The only one which has like in some situation comparable performance is RBS in the Amazon case. However, this structure doesn't work as well for the Facebook data set for several reasons, which I explained in the paper. Whereas like the learned ones overall actually perform very well over synthetic as well as rework workloads. So I highly recommend the paper here. And all the code as well as the benchmark results in newer ones are published on the web page at the bottom. There's also a question about theoretical guarantees. To address that, Paolo Ferragnino from the University of Pisa did some fantastic work, which actually proves that this, under some assumptions of the data distribution and so on, with high probability, learned structures are smaller than the traditional counterparts. Regarding updates and inserts, I unfortunately don't have time going into it, but there has been a bunch of work trying to address that. It turns out that in many scenarios, actually learned index structures can also better support inserts and updates. And you can think about that in the way, if your inserts follow similar distributions than what you have already trained over, you don't need to rebalance the tree, and it provides you a benefit. But one of the other key questions was just like, okay, how much does it actually help to use these structures? Because what I showed you before, they are twice as fast, but we were proving something which took like 200 nanoseconds to 100 nanoseconds. So you save 100 nanoseconds, which is not necessarily a lot. Of course, in some situations that might matter. So for example, if you do an index nested loop join, this actually can have a benefit because you do the lookup over and over and over again, millions of times, and then it actually adds up. However, it turns out that actually the smaller size is often a bigger differentiator. For example, learned index structures have been integrated into Google Bigtable, and they have shown to increase the performance by up to 50%, mainly because of the index size. The reason here is that in the case of Google Bigtable, often the index is larger than what fits into my memory and requires at least 1 IO to be fully loaded. So the top nodes of the index are into my memory. Then you traverse them. It points you to the bottom half of the index, which you need to fetch from disk. then you traverse that, which then points you to the final position of the data, which then requires another I/O to load it in. So now if you compress the index a lot, suddenly this whole thing fits into my memory and you save one I/O. And this is the reason where you see a performance benefit here. Something very, very similar has also been observed by integrating learned index structures into log-structured merge trees like RocksDB. Very similar reason. They also claim there has like other component effects, but like we still suspect that the big benefit actually comes from the size. So are there any limitations? Certainly there are. The most important one is if your data set has a lot of duplicates, actually the benefits degrade and learned structures perform more similar to the traditional one, right? You don't get the benefit anymore. And that's also easily explained by the fact that like if you have a lot of duplicates, how your CDF function actually looks like is that it has step functions in there. You have all the same value that's like, you know, in the CDF distribution, and then a new one starts, which steps up, and then it happens the same value again, and so on. Because of these step functions, it's just like it's very hard to approximate it using any linear functions or like any continuous functions, right? Like you have this like steps happening. What's the best way to approximate steps, or is like memorizing them, which in the end is what the decision tree or B tree does, right? So in that scenario, actually the benefits degrade. The other big downside is that we introduced a whole range of new knobs, but here's again where machine learning plays in, because you need to tune these structures automatically to make them work. And this is just like what models to use. It's like almost like meta learning in this case, right? You need machinery which automatically adjusts all the models and with it the index structures for the data you have. So this became a very, very active research area. What actually excites me is like the different types of disciplines, like learned structures by now have been applied. So on the right, there's just like, this is outdated, but it just shows you some of the publications happening around learned index structures. So those are just like really learned indexes, variants, not citations. These are like all new proposals about like somebody trying to improve this idea in one or the other direction or applying it to a new domain. For example, there was some work of like applying it to network packet classification and routing. We found work in like DNA sequence alignment using similar ideas, which were very promising and exciting. We saw it applied in like other system venues and like even operating systems. So like there's a whole range by now, which is very interesting overall. And we have this web page here at the bottom, which just lists a whole bunch of papers appearing not only for learned indexes but also other ML enhanced database data structures where you can just go and check them out. Okay. Moving on, unless there are any questions, I can stop here for a second.
Maybe a very quick question. This is very nice work. I remember back when I was in my postdoc at the lab of Philippe Coudreau-Marox. I'm not sure if you know him. So we were also discussing about this work, right? So there were a lot of discussions. So the question that I had back then was that, because you use machine learning here, but then what would be the worst case? But then later in your slide, you showed that, okay, actually there is a theoretical guarantee that it would never be worse than a B tree. But I was just curious. So can you elaborate a bit further on that? So yeah. How bad it can go?
That's true. So like in the original paper, we only looked into read optimized data structures, and for them it's actually pretty easy to provide worst case guarantees because you know the keys you have, you know the model you are using, so you can actually calculate the worst case prediction.
I see.
Right? And so in this case, you can strongly bound it, and then you can also build, like, I think in the original paper, we proposed hybrids. So if one model doesn't work as well, you replace that model using a B tree structure. And now you get something which is just like a hybrid between the two. Actually, if you use now the other proposals, like, for example, radix splines, they are built bottom up. So they fit linear functions or other functions through the data. which are guaranteed error bound, and then they index all these like different continuous functions on top of them, either using models again or something else. Right? And in this case, like it's also strictly bound because like how the training is done guarantees you how far you can be off in the prediction. It gets a little bit more tricky in the moment you have inserts. So Alex did some work on that. So Alex is an index structure which we have done together with Microsoft. The core idea is there that you actually retrain models over time, and then there's also a rebalancing step very similar to a B-tree in the worst case scenario. So that overall, again, I wouldn't say we have strong guarantees yet, but on average, it just works out. I think strong guarantees using learned models with inserts, I'm not sure if the PGM work actually did that, but otherwise, it's like still something which has to be done.
Yeah. Okay, thanks for the clarification.
Sure.
So I also have one additional question, and it's about this idea of the retraining. So if you have, a living data set essentially in your database that is continuously accruing data, you're going to have to re-index it at some point. And part of that re-indexing, obviously with this strategy, is you're going to need to then retrain these models. Is that ever considered in the comparison to the B-tree, which doesn't require any kind of retraining? In terms of like, you're going to get the efficiency, but you're losing the time aspect of all the retraining, right? So how does that kind of play into it?
So like the work which actually are concerned with instances, of course, consider that, but like it's a myth that B-trees don't require a type of retraining. So you can actually think that like the rebalancing is nothing else than retraining. And so like if you insert something, you have to shuffle things all the time around. And the question is, how often do you do that? And now you can have the pages half empty, which is a way to just delay that, but like eventually it will happen. This like reshuffling and rebalancing will happen. Right?
Very true.
Very similar, you can achieve something with models. So like Alex goes in that direction and tries to postpone that moment as much as it can, and then it actually triggers a retraining. That said, there's also something like what the B-tree doesn't do. So let's assume the following. I insert data always at the end. So like I index, let's say, a time column, and time usually is just increasing, right?
Mm-hmm.
So now in the B-tree case, if you don't do anything special, you would be inserting records always at one end of the tree, and it would cause a reshuffling constantly, rebalancing, because you only insert at one end. It's not the growing across all the items, right? It's just like you get very, very heavy on one side, which causes like, it's a worst case scenario essentially for inserting, right? So now let's assume for the second, instead you have a model which actually extrapolates into the future, because the patterns you observe going forward are similar to the patterns you observe in the back. So now in this case, you actually don't need to retrain your model because it generalizes hopefully to the future data in a much easier way. So just assume like a linear function even. You fitted the linear function over the past, probably the linear function always like also approximate the future in a certain way, right?
Sure, yeah.
And now you actually are better off because you do less retraining, rebalancing. So in some situations it might be worse, but I can also easily come up with scenarios where it's actually better.
True. Awesome. Thank you. That was a very good answer.
Sure. Okay, so let me move on here. So one very strong assumption I made in the previous work is just like all the data is sorted by the key we want to index. But normally, if we have some data, we always want to look up the data for like different types of keys. For example, let's assume we have like salaries and ages. You might want to look up the data based on like a query here, which just like looks into a range of it, right? So like, for example, I'm looking for records where my customers have a certain age range and a certain salary range. So if I don't have any sorting over the data, for this query, I would have to scan everything to get all the qualifying tuples, right? Let's assume like I sort by age or by salary. Of course, it gets a little bit better because now at least I can index one and I can just like pre-filter out a lot of them up front by using the index, but still I have to scan everything in this like red band because like only sorted by one dimension. So ideally what we want to do is just like given the workload, we want to come up with the right way to sort and lay out the data either in memory on disk as well as index it. one approach is that we apply a grid over it. And if we have this grid, now it allows us to prune out more data, which is guaranteed not like to qualify for our query. With this grid approach, now the core question becomes, how do we actually do layout the grid? And here, what we actually do is just like make it workload dependent. Right? So depending on the workload, we change on how we want to have this grid layout created. So if we make it more narrow, broader, and so on, and we use like the observed workload to figure out, okay, what's optimal for it. And then we can index this, let's assume like using learn structures or also other things. At the same time, if we just have one grid layout, we still have one problem, because maybe there's a pattern in the data which like it changes the organization from one moment to another. For example, if you have a dashboard, it's quite common that the queries over the last, let's say, months are very different than the queries over the last year. So we extended this idea of just like optimizing the grid layout in our latest work, which is called Tsunami, where you can like create complete different organizations for different pieces of the data. So we are very excited about this overall approach. So what I'm showing here is just like some performance results we have comparing Tsunami in blue against other types of like ways to organize your data and index it, including a clustered index, actually a hierarchical clustered index, where you just pick some hierarchy on how you do the sorting as one sort structure. A KD tree, which is a common multidimensional index structures, hyperarc trees, which is another common multidimensional index structures, z-order encoding, and FLAT, our previous work. What you see here on the x-axis is again the index size, and on the y-axis the query time. Where you want to be is the left bottom corner. And in this case, similar to before, we see like speed as well as size benefits, but this time in the range of really orders of magnitude in both query time as well as the index size. And now for SageDB, we actually built everything on this idea of like this multidimensional tuned data layouts as well as indexing over them, because we want to support the entire workload and not just like one dimension. Okay, moving on to another index structures, and like actually the last two Bloom filters and range filters, and let's see on how much time I have for query optimization. But like the Bloom filters and range filters, they had like some newer results which I find pretty exciting, and they're built on top of each other. So in the original work in 2018, we not only looked into how to replace B trees using models, but we also looked into other index structures, one being the Bloom filter. Right, so what the Bloom filter does is like it's giving you, like given a key, it asks you, is this key my set? If the Bloom filter says no, it's guaranteed that the key is not in the set. If the Bloom filter says yes, there might be false positives, meaning the key might be there or might not be there. So what we looked into is just like, can we not replace that using a model? And on one hand, you might be able to treat that as a classification problem. So given a key, is this in my set? And then use a classifier, which now says like yes or no. But if you use the normal classification algorithms, now you would get like false positives as well as false negatives. So you don't get the same semantic guarantees. However, there's an easy way to overcome that, and that is by, in the moment you have a no, you just put them through another Bloom filter, which just like filters out all the false negatives. And so if you combine this, now overall you can give again the same guarantees. Yeah. So what we thought is just like in some scenarios, we achieved like 36% space improvements over Bloom filters with the same false positive rate than their traditional counterparts. Similar to the indexing, this also became a whole research area on its own and has been improved by now by a bunch of different papers, which just like try to figure out on how to like get even better performance out of it. One interesting idea actually came from Michael Mitzenmacher, which showed that like if you first use the Bloom filter, then a model, and then a Bloom filter again, you get overall better guarantees. It's very counterintuitive. But he showed in his paper that like under certain conditions, this actually works better. And by now we actually improve on that further with an approach that we call partition Bloom filter, which also takes into consideration the certainty the model has when allocating the bits for the Bloom filter. So essentially, like if a model is very certain that the prediction is correct, it does do something different than if it's an uncertain prediction. So essentially, you take the certaintiness of the model into consideration if you have models which actually put out probabilities. So now, based on a similar idea, we started to address this question if we cannot improve range filters. So range filters is a newer concept. It's very similar to a Bloom filter, except that you can ask for a range. So for example, you can ask the question, is there a key between like A and B? If the range filter says no, you're guaranteed that there's no key in your set in that range. If it said yes, again, you might have false positives, but it's guaranteed that there are no false negatives. So in the past, how did people create these range filters? There are two state-of-the-art approaches. One is called SURF, which essentially builds a trie over all the keys in the set, and then trims it down to make it more like an approximate structure. So they just cut off some of the leaf nodes. Right? And in that sense, like if you now have a set, if you traverse it, if you cannot traverse it to a certain point, then you're guaranteed it's not in there. Otherwise, like if you end up to a leaf node, then it's a maybe yes, because there might actually be something following after which you don't know. So you have to look at the data. So it's one approach to achieve that. The other one is called Rosetta. What it does is just like it builds a bunch of like hash values. So like it looks the keys between the range, and then it builds a hash over every single key in that range with some spacing. And all the values are hashed. And then you use something very, very similar that you just like, okay, if I look everything between 100 and 200, now what I need to look up is all the possible hashes in this range. The downside of that approach is as bigger the range as you have, the more hash looks up you have to do. So we tried again to apply modeling to it, and it's very similar to the indexing idea that we build a model over the CDF of our data, and then we use the CDF model to actually set bits in a bit array. So it's important that the bit array is larger than the numbers of keys you have, because otherwise you might end up with just ones. But let's assume you oversize it. You have the CDF model. Now you put bits into this bit array by just setting them based on the CDF model. So now if a range comes in, is there like anything in between 13 and 15? What you do is just like use the same CDF model, which points you to two places in the bit array. And then if any bit is set in between, you know that there's potentially a key there which matches. Okay? If there's no bit set, then you're guaranteed there shouldn't be one, under the assumption, of course, that the model is monotonic. That's a very important assumption here. So you need a monotonic model. So there are two things you need to make sure. One is that the model is monotonic. And the other thing is like you need to figure out a way that all the bits you have there are actually compressed, because you don't want to have this giant bit array out there. And so for this one, you can use delta encoding, for example, which just stores on how many zeros you have between the different points. What we use in the paper recently is Golem encoding, which actually you can show it's optimal in the case that the bits are evenly spaced in between. Yeah? So like if the CDF would be perfect, Golem coding would be the best possible choice as well. So now comparing our learned range filters with the traditional ones. So here we have a comparison between Rosetta, Surf, as well as SNARF, which is our long-based approach. So that's the name of it. And then like cuckoo filter, which only work for just traditional point queries. What we show here on the far left is the point queries. So just looking up a single key. With the range filters, you can just do the same thing as the Bloom filters by just having A and B, the range you're looking up being the same key, right? So this makes it essentially point lookup, then range lookup, and then a mixed workload on the right. On the x-axis is the space used, the bits per key. On the y-axis is the false positive rate. So where you want to be again is the left bottom corner. And what you see is actually that SNAF performs pretty well across the board regarding the space for positive rate trade-off. We also integrated SNAF actually into a real system called RocksDB, again, very similar what we saw before, and found that compared to Rosetta and Surf, if SNAF is used as a range filter in the setting, it actually has a very positive impact of the overall execution time, because with less bits, it can have a better false positive rate and prune out or prevent more unnecessary IOs. And we use the same setup as like other papers did before, like as found in Rosetta, for example. Okay, so the last one, I just want to give like an indication around like query optimization, just like as a, before I start to wrap up and show you some results of SageDB. So what we also looked into is just like SQL query optimization. So if you're probably all familiar with a query optimizer, does the following: takes a SQL quiz, it passes it. Then you have like a traditional like cost model normally, which then decides, okay, what should be the join order and what operations to use. Then this thing gets executed and you get a result back. In the traditional sense, unfortunately, there's no feedback loop, meaning if the query optimizer makes a mistake, it doesn't learn from it. And it doesn't remember how to correct it the next time around. So our first attempt actually was to replace the entire thing using a model. We called it the Neural Optimizer, or NEO, where we actually trained a deep learning net to just replace the entire query optimizer. This worked and it gave good performance over time, but the training time was very, very high. Plus the decision it makes was hard to understand. And like we thought this actually is not practical, because even changing the schema in any way would, at least with our first model, trigger an entire retraining. So we went back to the drawing board and we actually proposed a new approach called BAO, with the idea of like leveraging all the knowledge which is built into traditional query optimizers, but then create a way to improve them over time. And so how we do that is like we have the traditional optimizer, but then we also create variants of that using hint sets. So for example, we say, please don't use nested loop joins, only use hash joins, and so on. So we provide hints on what features to turn off or turn on in the query optimizer. Okay. And then we build all this machinery to figure out over time what hints to use for what types of queries. So in the end, this is very, very similar to what a database administrator would do. A database administrator looks at the queries, sees the worst performing ones, and then tries to figure out the right hints to set for this query to steer it in the right direction when it gets re-executed. Right? So like a database administrator normally figures out what hints to use for what types of queries when something is not performing in the right way. And this is what we are doing now here as well. We're just learning that automatically over time. The big advantage of that approach is like it allows us to install BAO, our learning-based hint generator, on top of other systems without changing the system itself. So we actually use BAO on top of Redshift, SQL Server, Vertica, DB2, and this is really running BAO in front of the traditional system, but use the traditional system then to execute all the queries. And what we see across the board for different workloads is actually a cost and time benefit of up to, let's say, 30 to 50%. Yeah. We also used it on top of Postgres. We see like big benefits. We compared it to NEO. NEO actually eventually does better. So the full like learned approach does better because it's not restricted by the hints the system provides and has more degrees of freedom. But like as you can see here on the left time, it shows like the time it takes until one approach becomes better than the other. It takes much, much longer until the green line passes the blue one, whereas the blue one immediately is better than the yellow one, which is the Postgres original optimizer. BAO also has been, or the ideas of BAO have been used at Microsoft. with very promising results. So this is a citation. So by using this approach, they saw like benefits of up to 70 to 30% on average, but 90% improvements on non-trivial sets of the workloads. So of course, if you just have a filter condition, there's not much you can do. The query optimizer normally doesn't do much. It's more complex the queries get, the higher the chance that the optimizer also screws up, the more important our approach actually becomes. Okay, so given that we are a little bit short on time, let me very, very briefly talk about SageDB. So the core idea is just like what I showed you so far as how we improve a single component of a database system. So we started out with access methods, which is just like, let's say, indexing, and we spent a whole ton of time on that. Other people looked into dispatching and scheduling. I showed you some results on query optimization, but if you have this like traditional database architecture, each of these boxes, each of these components it has, I can name you at least one paper or component where somebody already figured out a way to make it ML enhanced. Right? However, all these components so far have been done in isolation. So as I alluded to in the beginning of my talk, it's just like ideally we want to bring everything together to build the first really end-to-end instance optimized system. So this is what we are trying to do with SageDB. It's our first attempt to build something more end-to-end. We integrated it into Postgres as an accelerator, but eventually this will become a standalone database. Right now, it's just like it's an accelerator to Postgres where you can say like, okay, I want to have an external table, which is then completely managed by us. And as more external tables you have managed by us, we do all the stuff for you in this environment, but we still give you the full flexibility of Postgres and with all the functions they have. So if we don't support something, we fall back to Postgres. So these are like some very initial performance results using one of our workloads based on Bitcoin data. What it shows you on the left is like the overall latency to execute the workload. On the right side is like the size the data takes. We compared SageDB against Postgres as well as a commercial column store, an analytical database. And in two modes, standard tuning, which is essentially out of the box after tuning every parameter in the way you're supposed to, and then expert tuning, which actually having somebody who's an expert in the system, really looking into the data and the workload and tuning every parameter in the best possible way. What you see here is that SageDB in regard to execution time is orders of magnitude faster than Postgres, but also like significantly faster, like almost a factor 10x than the commercial database. However, at a fraction of the cost. For example, on the right side, we see the overall size. What happens is like the version where the commercial analytical database gets the closest, like let's say a factor of 6 to 7x from SageDB, is by creating a whole range of materialized views. Right? So like here, a whole range of materialized views created, which then gives you the performance, but at the cost of like a lot of additional memory required. So overall, we think this is like a very encouraging result, and we are heavily working on it. Like this one actually didn't include a whole range of new optimizations, which we recently did around partial materialization result, memory hierarchy optimizations, multidimensional indexing, and so on. And we currently have a paper under submission, which has like some of the newer ones in there. If anybody is interested, I'm more than happy to send a pre-draft. Okay. Last, before I conclude, is just like a little bit about future directions. So if you're thinking of entering this field, I only can highly encourage you. I strongly believe that we are still only at the beginning of it, of leveraging machine learning to improve systems. There are tons of open issues. There are a bunch of potential showstoppers. So often I say like it's often if you think about applying it, it feels like a very little step to achieve an instance component, and then you sink in and it actually turns out to be much more complicated than you thought. And there are some potential showstoppers. Like one of the biggest like limitations we often see is the access to data sets and workloads. So when you start doing that, you will quickly notice that benchmarks are either too easy because they all have synthetic data, or actually too hard because it's all synthetic data and there's no interesting pattern in them. It's all random. right? And so it's either or, but it's never good. And so really doing something, you need real work data, and we're heavily working on that. We can also hopefully create a repository of them and make them public. But for now, there's not much around there. There are also things around like working with the communities, but overall, I think this is a very, very exciting like area right now, not just like in database systems, but also we see like exciting work happening in the theory field, which like often talks about like algorithms with oracles and just approaches more from a theoretical perspective. There's stuff happening in the networking community as well. We also see like some of our papers already now published in machine learning communities. So it's a very interesting field where you actually can work across different areas. Regarding picking topics, like I always say, they're like the obvious choices. So if you have a heuristic already in your system, probably the heuristic is not always the best choice. So you can just figure out a way to learn it. But then there are also like less obvious choices where you already have a solution which is like known to be sub or linear in runtime for space complexity. Like indexing is actually log n used to be pretty good, but still under certain conditions, it turns out that there might be surprising results and possibilities there. Whole range of open questions, particularly regarding robustness, worst case guarantees, implications for modern hardware. For example, like what these structures often do is like trade if statements for math operations, which are often better suited for GPUs and some of these like newer hardware types, which is also interesting, and so on. Okay, with that, I'm at the end of my talk. I just want to do a big shout out to all my postdocs and students. Without them, all this work wouldn't have been possible. And I'm more than happy to take one or two more questions if there are any. Thanks a lot again for having me here. It was really a pleasure.
Thank you, Tim, for sharing your work on this very exciting new field. Do we have any questions from the audience? You can just open your mic and speak. Eh?
Yes. Hi. Hello.
Hi.
Can you listen to me? Yes. Hi. I'm Ziyu and also working in TU Delft. So thank you, Tim, for a really interesting talk. I have a question. Well, I actually have two questions. So the first question is that you apply machine learning in the field of database, for example, to improve the techniques in the database field. And how do you think of the management of models? Because you need to train a lot of data, you need to manage the training data, right? And also you have to manage the models. Is that a concern during in your work?
It depends a little bit. So it depends on which component you're talking about. In the case of indexing, for example, the training data is the data you have stored. So in this case, it's you already have it, you already store it. It's trivial to just use it, right? And managing the models is like the same thing as retraining the index structure or rebalancing a B tree, right? So like it's built into the component. On the other hand, if you have query optimization, what you just mentioned fully applies, right? Because it's just like now you have models for the query optimizer. If you roll out one model over another, it might have implications for different users. So far, I know not many people have looked into that. It's definitely an open area on how to best do it. And yeah.
Yes, and actually my research topic, I'm also a PhD candidate. My research topic is actually a little bit related to what you do, but on the opposite. So you're working for ML for DB, but I'm working for like using database technology to improve machine learning inference. And so I'm wondering, what's your point regarding like, I mean, these two aspects? Do you feel like there's any like relations, or is there anything that you suggest as a interesting topic?
That's also a good question. I have to say, I haven't really deeply thought about it yet. Like, I think ideally, if you, so I was always a little bit skeptical to integrate like machine learning capabilities into a database, right? Like particularly like, and it depends a little bit on what type of capabilities you're talking about, because like it's, if you see data scientists working with data, they are now all in the Python environment. and they don't want to suddenly have necessarily their models running inside the SQL query, right? This doesn't fit their workflow. That said, I also learned from a large analytical database provider that they actually have this feature, and that some people really like it because like the users then don't have to think about the size of the data anymore. It just magically works. Right? So like I don't have a full handle on that yet. I think ideally it would be great to have one programming environment which is deeply integrated into the database, which is then also used to maintain all the models the database itself uses to get like instance optimized. It's a grand vision, but like we are struggling already so much getting one direction right. I think we are far away to getting both directions and have everything integrated into one right. So like it will take time. It's hard to say for me, but like I also know like the Python environments are very dominant right now. Like it's like it became the de facto standard, right?
Yes. Yes. Thank you, Tim. Thank you for your answer. Yeah.
So very quick, shameless advertisement, team. We're working a lot on database for machine learning. So I can share with you some of our recent work. But Tim, would you be still available to take one more question?
Sure.
Okay. So I have a question about these many different parts of the database management system that you can optimize, right? Some of them are more are closer to the data stored in the system. Some of those are more on the meta level, I would say. For example, this scheduling, right? I was wondering, so how would this like a lot of those learning, you need to collect a lot of data first, right? But if you go beyond the smaller parts but try to optimize the whole system, you would need much more data about user behavior. I don't know, huh? So just some thoughts that I have, but I'm not sure if you have something to.
Yes, I mean, like that's certainly true. Like, so indexing, for example, to take it as a case, it's very simple because you can get a bunch of like static data sets, and getting a data set nowadays is relatively easy, and you can try it out, right? And you know that everything has to be trained from scratch for a particular data set, and it's fine. Let's assume like query optimization, on the other hand, is actually a little bit more tricky, because ideally what you want to have is not only the data, but also different types of workloads, so that you can figure out what type or what part of the query optimizer you can actually transfer from one database to the next to create something which is more generalizable, but then also enable this fine-tuning in the end, so that you, for example, learn the best possible cardinality estimates for the particular data set you have, right? And here data and access to workloads becomes a real challenge. So we so far, like, we either created our own workloads, and we were lucky to get some real ones from like some of our collaborators, but it's still a struggle. I think eventually, like the right places to do that are the ones who are like cloud providers of database services. You know, they are like Google, Microsoft, Amazon, Snowflake. Those have all the tenants, they see all the workloads, they have the data, and they will, with other machine learning type, they will have an edge.
Yeah, indeed. Thanks for sharing. This is all the questions that we have. So thanks again, team, for the inspiring talk and also the great discussion. It was a great pleasure to have you here. Thank you so much.
Thanks again for having me. This was great. Thanks.
Thanks everyone for joining the Academic Fringe Festival. So in 2 weeks, we will have Vanessa Murdoch speaking about quality in e-commerce and beyond. So see you next time.
Thanks. Bye.
Bye.